Chapter 4, Part 2, Data Acquisition Concepts. The components of the X-ray system for a CAT scanner include the generator, the tube, the beam filter, and the collimators. And we will start by discussing the generator, which uses three-phase power. It uses high-frequency generators. They are small and compact and located inside the gantry. In the past, the generators were big and bulky and located in the corner of the room, possibly, and a long high-tension cable ran from the generator to the X-ray tube in the gantry. The circuit is called the high-frequency inverter circuit. Low voltage, low frequency current is used from the main power supply, and it is converted to high voltage, high frequency current. And this happens as it passes through the components. Each component changes the low voltage, low frequency AC waveform to supply the X-ray tube with the high voltage, high frequency direct current of almost constant potential. And after the high voltage rectification and smoothing occurs, the voltage ripple from a high frequency generator is less than 1%, compared with a 4% from a three-phase 12-pulse generator. The X-ray exposure technique obtained from these generators actually depends on the generator power output, and these power ratings vary from vendor to vendor. Since spiral or helical CT scanners rotate continuously for long periods of time as compared to conventional scanners, the component design must be able to deal with issues such as those that are in regards to heat generation, heat storage, and heat dissipation. A glass envelope is part of the X-ray tube, and it ensures a vacuum, which provides support of the anode and the cathode structures, and provides high voltage insulation between the anode and the cathode. It includes internal getters, which are also known as ion pumps, and these remove air molecules to ensure that the vacuum is sustained. Borosilicate glass provides good thermal and electrical insulation, and the electric arcing results from the tungsten deposits on the glass caused by vaporization. Tubes with metal envelopes do not have electric arcing. The ceramic insulators isolate the metal envelope from the anode and the cathode voltage, and they have larger anode discs than the conventional tubes. This allows for the usage of higher currents and increased heat storage capacity. Regarding the cathode assembly of the X-ray tube, it consists of one or more tungsten filaments positioned in a focusing cup. The internal getter is actually made of barium for the cathode assembly, and it ensures the vacuum by absorption of air molecules released from the target during the operation. It contains a filament, which is a small coil of a tungsten wire, and this is where electrons are emitted. So right here in the filament is where the electrons are emitted. The focusing cup is a small depression that houses the filament. So this is a picture of the anode assembly of the X-ray tube. It consists of a disc, a rotor stud and hub, a rotor, and the bearing assembly. There are three basic designs for anode discs. The first one is an all-metal disc, and this type of design is used in conventional scanners. It's made of titanium, zirconium, and molybdenum with a focal track layer made of 10% rhenium and 90% tungsten. And you can transfer heat from the focal track layer very quickly with this type of design, but it's not useful for the spiral helical scanners due to its weight. The second type of anode disc design is the brazed graphic disc, which is made of tungsten rhenium focal track brazed to the graphite base body. It has 10 times greater of a heat storage capacity than tungsten. And most spiral helical CT scanners actually do have this design. The third type of the anode disc design is the chemical vapor disposition graphite disc, and this is made of a graphite base body with a tungsten rhenium layer deposited on the focal track by a chemical vapor process. It has a large heat storage capacity and fast cooling rates. And this is also used in spiral helical scanners. In the anode assembly, there is the bearing assembly, which provides and ensures the smooth rotation of the anode disc. And the bearing assembly was actually noted in the picture a few slides back. It allows for high rotation speeds. The high-speed anode rotation allows for the use of higher loadability in CT, and then these high rotation speeds are possible with the increased frequency to the stator windings. But smooth rotation of the anode disc are possible because of the ball bearings that are lubricated with silver. And because the ball bearing technology results in mechanical problems and limits X-ray tube performance, a liquid bearing method was introduced to improve the anode disc rotation. The anode assembly also includes the rotor hub and the rotor stud, as we previously mentioned. And this prevents the transmission of heat from the disc to the bearings. The rotor is made of a copper cylinder that's brazed to the inner steel cylinder with a ceramic coating around the outside to enhance the heat radiation. As we've previously discussed, the basic problems with conventional tubes deal with heat dissipation and slow cooling rates. And that holds true for even some of the multi-slice CT designs that have longer scan times and when performing cardiac imaging. To overcome these issues, a new type of tube was designed for use with the multi-slice CT scanners, and it was actually designed by Siemens. This is the Stratton X-ray tube, which is encased in protective housing that contains oil for cooling. It is much smaller than conventional tubes, and the small size actually ensures that the gantry will rotate faster. It has anode and cathode structures, deflection coils, and an electron beam, as well as a motor. The electron beam produced by the filament housed in the cathode assembly is deflected to strike the anode to produce X-rays used for imaging. The motor actually provides the rotation of the entire tube, which is immersed in oil. The anode is in direct contact with the oil, so it is directly cooled. And then because the anode is in direct contact with the circulating oil, very high cooling rates can occur. High-speed volume scanning is possible with high MA and long exposure times for increasing the length of anatomic coverage in the Stratton X-ray tube. Radiation from X-ray tubes consists of long and short wavelengths. The beam is polychromatic, which means it has a broad spectrum of X-ray energies. However, it is very important that the polychromatic beam has the appearance of a monochromatic beam to satisfy the requirements of the reconstruction process, so a special filter must be used. Filtrations remove the long wavelength X-rays from the beam, and then the mean energy of the beam then increases, which makes the beam harder. And this may cause beam hardening artifacts. Remember, beam hardening increases the average energy of the X-ray beam by filtering out those low energy photons. Total filtration is found by taking the inherent filtration plus the added filtration. Inherent filtration has the thickness of about 3 millimeters of an aluminum equivalent. And added filtration consists of filters that are flat or shaped. For example, you may have heard of a bow tie filter. These are made of copper sheets, and the thickness can range from 0.1 to 0.4 millimeters. Filtration shapes the energy distribution across the radiation beam to produce a uniform beam hardening when the X-rays pass through the filter and the object. I want you to go over figure 425 in your book. You can see that the attenuation is different in sections 1, 2, and 3, and then that the penetration increased in sections 2 and 3. This results from the absorption of the soft radiation in sections 1 and 2, which is referred to as hardening of the beam. Collimation is extremely important in CT because it affects patient dose and the image quality. Collimation in CT includes pre-patient, post-patient, and pre-detector collimators. They must be perfectly aligned to optimize the image process, which is achieved by fixed collimators. With the pre-patient collimator design, it is influenced by the size of the focal spot of the tube. due to the penumbra effect associated with the focal spots. So the larger the focal spot, the greater the penumbra, and more complicated is the design of the detectors. CT detectors capture the radiation beam from the patient and convert it into electric signals, and they are then converted into the binary coded information. Detectors have many characteristics that are essential for CT image production that affect good image quality, such as efficiency, response time, dynamic range, accuracy, stability, resolution, crosstalk, and afterglow. Efficiency is the ability to capture, absorb, and convert X-ray photons to electric signals. CT detectors must have a high capture efficiency, absorption efficiency, and conversion efficiency. Capture efficiency is the efficiency that detectors can obtain the photons transmitted from the patient. The size of the detector area facing the beam and the distance between the two detectors determines capture efficiency. And absorption efficiency is where the number of photons are absorbed by the detector. So this depends on atomic number, physical density, size, and thickness of the detector face. Stability is known as the steadiness of the detector response. Frequent calibrations are required if the detector is not stable. Response time is the speed at which the detector can detect an X-ray event and recover to detect another event. This should be very short in order to avoid problems such as afterglow. Dynamic range is the ratio of the largest signal to be measured to the smallest signal to be measured. And this is about 1 million to 1 for most scanners. Afterglow is the persistence of the image even after the radiation has been turned off. There should be low afterglow values, so you want to keep that afterglow minimized. Resolution is influenced by the detector element size, focal spot size, and the sampling size. Crosstalk occurs when one detector element leaks over into an adjacent detector. Okay, very important. We will now discuss the CT detector types. There are 2 of them. First is the scintillation detector. This includes solid state detectors that consist of a scintillation crystal coupled to a photodiode tube. So when the X-ray falls into the crystal, flashes of light, which are called scintillations, are produced. The light is then directed to the photomultiplier tube. When the light strikes the photomultiplier tube, electrons are released and they cascade through a series of diodes that are carefully placed to result in a small signal output. The scintillation materials currently used with the photodiodes are cadmium tungstate and a ceramic material made of rare earth oxides. These crystals are usually optically bonded to the photodiodes. The conversion efficiency and the photon capture efficiency of the cadmium tungstate are 99% for each, and the dynamic range is 1 million to 1. And then the absorption efficiency of ceramic rare earth oxides is 99%, and its scintillation efficiency is 3 times what it is for the cadmium tungstate. In gas ionization detectors, these are based on the principle of ionization and were introduced in 3rd-generation scanners. They consist of individual gas chambers separated by carefully positioned tungstate plates, and these actually act as electron collection plates. With this type of detector, xenon gas is usually produced when the X-rays fall on the individual chambers, and this produces positive and negative ions. Positive ions migrate to the negatively charged plate, and the negative ions go to the positively charged plate. This migration of ions causes a small signal current that varies directly with the number of photons absorbed. Xenon detectors have excellent stability and fast response times and exhibit no afterglow issues. However, their quantum detection efficiency is less than that of the solid-state detectors. One major problem with single-slice, single-row detectors is the length of time it takes to acquire all the data in an exam. The dual-slice, dual-row detector system was developed to increase the volume coverage speed, which also decreases the time necessary for data collection. CT scanners now use multi-row detectors to image multi-slices during a 360-degree rotation. Dual-row, dual-slice detectors were first introduced in 1992. They result in faster coverage than the single-row CT systems. This technology uses a dual-row solid-state detector array coupled with a special X-ray tube based on a double dynamic focus system. The dynamic focal spot is where the position of the focal spot is switched by a computer-controlled electron-optic system during each scan to double the sampling density and the total number of measurements. Twin beam technology results in the simultaneous scan of two contiguous or touching borders of slices with excellent resolution, since the fan beam, ray density, and detector sampling are doubled twice, one for each of the two contiguous slices. The goal of multi-row, multi-slice detectors is to increase the volume coverage speed even more than the dual-row, dual-slice scanners. They are known as MRMS detectors, and these type of detectors are made of one detector with rows of detector elements. A detector with, let's say, 5 rows will be 5 times faster than its single row counterpart. These type of detectors are solid state detectors and can acquire 4 to 64 to 320 slices per 360-degree rotation. Also, the design of these detectors can influence the thickness of the slices. Multi-row, multi-slice detectors, they have an array consisting of multiple detector rows. So for example, these detector rows can range from 2 to 64 detector rows that can image simultaneously 2 to 64 slices per 360-degree rotation. The number of slices obtained per rotation depends on the number of detector rows. For example, a 16-row detector can produce 16 images per 360-degree rotation. There are 2 categories, the matrix array, which is also known as the fixed array detectors, and adaptive array detectors. The fixed array detectors have an isotropic design, and they contain channels or cells that are equal in dimension. The isotropic imaging produces improved spatial resolution in longitudinal and transverse planes. The adaptive array detector, includes an anisotropic design, and the cells are not equal, but they're actually different sizes. Take a look at figure 440 in your book for these 2 different types of categories. So now we will discuss the 3 functions of the data acquisition system. The data acquisition system refers to the detector electronics positioned between the detector array and the computer. It performs 3 functions, which are measuring the transmitted radiation beam, encoding these measurements into the binary data, and transmitting the binary data to the computer. So first you have the detector that measures the transmitted X-rays right here from the patient and converts them into electrical energy. But the electric signals are so weak that it must be amplified by the preamplifiers before it can be analyzed any further. Take a look at figure 444 in your book. The transmission measurement data must be changed into attenuation and thickness data, and this logarithmic conversion can be expressed by the formula thickness times the log of the transmission equals attenuation. The logarithmic conversion is done by the logarithmic amplifier, and these signals are then directed to the ADC. The ADC divides the electric signals into multiple parts. The more parts, then the more accurate the analog to digital conversion is. These parts are measured in bits. A 1-bit ADC divides the signal into 2 digital values. A 2-bit ADC generates 4 digital values, and a 12-bit ADC results in 4,096 digital values. These values help determine the grayscale resolution of the image. Modern CT scanners today use the 16-bit ADCs. The final step performed by the data acquisition system is data transmission to the computer. The CT manufacturers have introduced optoelectronic data transmission schemes for this purpose because of the continuous rotation of the tube or the detector arc and large amounts of data generated. Optoelectric just means that it uses lens and light diodes to facilitate the data transmission. Several optical transmitters send the data to the optical receiver arrays so that at least one transmitter and one receiver array are always in optical contact. These receivers and transmitters are light emitting diodes capable of very high rates of data transmission.